Welcome to this session. In this class, we will be looking into the standard eigenvalue problem or the Sturm-Louiville problem and its property, and we will be looking into a generalized problem. Let us consider the operator, general operator L as Lu equal to a0 x d square u dx square plus a1 x du dx plus a2 x u. So, let us consider this operator, and on separation of variable we may be getting a relationship like this. A0 u double prime plus a1 u prime plus a2 u plus lambda a3 u is equal to 0, and where lambda is a constant. Let us assume the Dirichlet boundary condition that at x is equal to 0 and x is equal to 1, we have u is equal to 0. Now, this equation can be written in a compact form as Lu plus lambda a3 u is equal to 0, or it will be written in the form of Lu is equal to minus lambda a3 u. Now, if you look into the formation of this equation, the form of this equation, the equivalent notation in the matrix algebra in the discrete domain. This is a continuous domain, we are talking about the functions, continuous functions. Now, in the discrete domain in the matrix, if you look into the similar form of equation, similar form corollary is that for matrices, the similar type of equation we can see as Ax is equal to lambda x, and this is known as eigenvalue problem. Therefore, in case of the continuous domain for functions, this is a standard eigenvalue problem. Okay. So, let us consider this is a equation 1. Now, this equation 1 can be rewritten in this form, means equation 1 can be rewritten as d dx of px du dx. Okay, so this is the end of it, plus q x u plus lambda r x u is equal to 0. Now, this equation can be written in this form, where we will be defining px, qx and rx in terms of the original coefficient a0, a1, a2 and a3. So, let us define that px is nothing but e to the power integral a1 x divided by a0 x dx, qx is equal to a2 x over a0 x times p, and rx is equal to a3 x divided by a0 as a function of x times p. So, if you define, so you just this equation can be if you define these quantities p, q and r in the equation number 1, then you will be getting back the equation 1. This is very simple, very simplified case. So, if we take the logarithm of both sides and then differentiate, so ln p is equal to integral a1 x divided by a0 x dx. So, if you differentiate it, so you will be getting dp dx 1 over p is equal to a1 by a0, and similarly qx is given as a2 by a0 times p, and if you just put it back, you will be getting of the governing equation. So, I just establish the identity of both the equation to be same, p du dx plus q u plus lambda r u, this becomes p d square u dx square plus dp dx du dx plus q u plus lambda r u. So, just substitute p, the p is just as leave it as p. Okay. So, if this is the equation, right, this is the equation, then we will be getting p d square u u double prime plus dp dx. dp dx is nothing but a1 by a0 times p plus q is a2 by a0 times u plus there will be a p there, q in the lambda, r is a3 by a0 times p u is equal to 0. So, p will be cancelling out from each step, and then you multiply both sides by all sides by a0. So, what you will be getting is that a0 u double prime plus a1, there will be a du dx here. So, a1 u prime plus a2 u plus lambda a3 u is equal to 0. So, these two equations are identical. So, this will be giving you L u is equal to minus lambda a3 u. So, substituting p q r by defining p q and r, this equation number 1 is equivalent to this equation. So, these two equations are identical. So, let us see what do we get out of it. So, Lu is now becomes d dx of p d dx plus q multiplied by u. So, therefore, px u double prime plus dp dx u prime plus q u is equal to L u. So, L is now becomes d dx of p d dx plus q. Okay. Now, earlier we had if L of v is equal to a0 v double prime plus a1 v prime plus a2 v, then L star v will be nothing but a0 v double prime plus 2 a0 prime minus a1 v prime plus a0 double prime minus a1 prime plus a2 times v. This we have already proved earlier. In the last class we have proved this. Now, if you compare a0, a1 and other things, so if you compare this equation number 3 with 4, that we have already seen earlier that a0 is nothing but p of x, therefore, a1 is nothing but dp dx and a2 is equal to q of x. So, L star v is nothing but p v prime double prime plus 2 p prime minus p prime times v prime plus p double prime minus p double prime plus q is equal to into v. So, therefore, this becomes p v double prime plus p prime v prime plus q times v. So, therefore, you can always see that L star is equal to L. So, L star will be nothing but, what is L star? L star is p d square dx square plus dp dx times p prime d dx plus q. So, this will be nothing but d dx of p d dx plus q. So, if you see that L is equal to nothing but L star. So, L is equal to this and L star is equal to this. So, L is equal to L star and our general Sturm Louiville operator or eigenvalue operator is a self-adjoint operator. Operator in general is where L is equal to L star. Now, we will see that to prove B is equal to B star, and if we want to prove B is equal to B star, we have to check, let us say, a generalized boundary condition. Consider a generalized boundary condition. This will be no longer a directional boundary condition. Consider a generalized boundary condition that at x is equal to a, we have alpha 1 u prime plus alpha 2 u is equal to 0, and at x is equal to b, we have beta 1 u prime plus beta 2 u is equal to 0. And then we will be looking into the bilinear concomitant. If we look into the bilinear concomitant, this becomes v a 0 u prime minus v prime a 0 u minus v a 0 prime u plus a 1 v u evaluated on the two boundaries a and b. Now, we have already proved that a 0 prime is equal to dp dx is nothing but p prime is equal to a 1, and a 0 is equal to p and a 0 prime is equal to a 1. So, bilinear concomitant now becomes only, it boils down into a 0 times v multiplied by u prime minus v prime multiplied by u, whole thing evaluated between a and b. Now, if you really do that and substitute the values, let us see what the bilinear concomitant will give us. So, j u v is nothing but a 0 at b, v at b, u prime at b minus a 0 at b, v prime at b, u at b minus a 0 evaluated at a, v at a, u prime at a minus minus plus a 0 at a, v prime at a and u at a. We already had the boundary condition of the original problem as that at x is equal to a, we had alpha 1 u prime plus alpha 2 u is equal to 0. So, we can substitute at x is equal to a, u prime at a. So, u prime at a we can substitute, and then at x is equal to b, we have beta 1 u prime plus beta 2 u is equal to 0. So, we can substitute these two. So, j u v will be nothing but a 0 at b, v at b, and u prime at b will be nothing but minus alpha 2 by alpha 1 u at b minus a 0 at b, v prime at b, u at b, and minus a 0 at a, v at a, and u prime at a we substitute. Okay, this was u prime at b. So, this will be beta 2, this will be nothing but this will not be beta alpha 2, this is beta 2 and beta 1, and u prime at a will be alpha 2 minus alpha 2 by alpha 1 times u at a minus plus a 0 at a, v prime at a, and u at a. Now, we can collect the terms. For example, we can take a 0 b and u b common from this one, from the first two terms. So, if you really do that, a 0 b and u at b, we take it common. So, what is remaining is minus beta 2 by beta 1 v at b minus, we can take minus also common from first two terms. So, it will be plus beta 2 by beta 1 v at b plus v prime at b, and we can take a 0 a as common, minus minus plus. So, it will be plus a 0 at a common and v and u at a common. So, if you do that, what we will be getting is alpha 2 by alpha 1 u at a plus v at a, the plus v prime at a. Now, if I select this equal to 0, this boundary, at this boundary x is equal to b, and at this boundary x equal to a, this whole thing is common. Let us see what you get. In order, so if we really select that, then bilinear concomitant will vanish. So, at x is equal to a, if we select alpha 2 v plus v prime a divided by alpha 1 is equal to 0. So, that will give me alpha 1 v prime plus alpha 2 v is equal to 0 at x is equal to a, and at x is equal to b, I will be getting beta 1 v prime plus beta 2 v will be 0 to make bilinear concomitant to vanish. So, this will be now my B star or boundary condition of the adjoint problem. Now, we see that B is equal to B star, and we have already proved L is equal to L star for a generalized eigenvalue problem. So, the standard eigenvalue problem operator is a self adjoint operator. So, a 0 d square dx square plus a 1 d dx plus a 3 a 3. So, this will be, if this is the form, then L u is equal plus lambda a 1, this will be a 2 plus lambda a 3 will be 0. So, this is a standard eigenvalue problem, and in this standard, this is a generalized form of standard eigenvalue problem, or it is also known as the Sturm Louiville problem. And we have proved that a Sturm Louiville problem is nothing but a self adjoint problem. So, L is equal to L star and B is equal to B star in this particular case, and we are having a self adjoint operator with us. Now, by establishing the Sturm Louiville problem or standard eigenvalue problem is a self adjoint problem, a self adjoint operator, then let us see what are the various properties of the self adjoint problem we can exploit for using separation of variable. Now, there are certain salient problems of the standard eigenvalue problems are there for the self adjoint operator. The important properties of self adjoint operators operator we should look into. So, the first property that goes as a theorem number 1 is that there is a countable infinite number of eigenvalues present for a Sturm Louiville problem. So, the number of eigenvalues present in the system is infinite in number. So, therefore, we will be talking about a infinite dimensional space, and it is basically a continuous function having infinite dimension. So, number of eigenvalues will be infinite and number of eigenfunctions will be infinite. Then the next important theorem is that if phi m, this is the corollary 1, is that if phi m and phi n are orthogonal with respect to weight function R x. So, this is a definition of orthogonal functions. Phi m and phi n are the two functions which are said to be orthogonal with respect to each other and with the weight function R. Then if this equation is satisfied, integral a to b R x multiplied by phi m multiplied by phi n dx is equal to 0. So, for m not is equal to n. So, this is known as the orthogonality condition. So, next what we will be showing next theorem, that for if lambda n and lambda n are the two distinct eigenvalues of the Sturm-Louiville problem with the eigenfunctions y m and y n, then y m and y n are orthogonal functions with respect to weight function R. So, let us look into the theorem and look into its proof. So, next theorem which will be quite important to us is that if lambda m and lambda n are two distinct eigenvalues, this is important, two distinct eigenvalues with eigenfunctions y m and y n, then y m and y n are orthogonal functions with respect to weight function R x. So, let us prove this theorem. So, proof goes like this: the Sturm-Louiville equation becomes L y is equal to minus lambda R y, where R is a function of x subject to boundary condition b is equal to 0, where the domain of x lying between b and a. So, since lambda m and lambda n are the eigenvalues with the eigenfunctions y m and y n, they will be satisfying this equation. So, I can write L y n is equal to minus lambda n R y n. L y m should be is equal to minus lambda m R y n. Then what we will be doing? We will be multiplying equation 1 with respect to y m, multiplying equation 2 with respect to y n, and integrate and subtract. So, what I will do next is integral of y n L y m dx minus y m L y n dx. Okay. So, this becomes minus lambda m R y m y n dx minus minus plus lambda n R y m y n dx. Okay. So, we will be getting on the right hand sides as lambda n minus lambda m integral R y m y n dx. So, next what we invoke the property of the adjoint operator, and if we look into the property of the adjoint operator, that integral of u L v is nothing but integral of L star u v plus j uv. We utilize this property and we put down the first integral yn L ym dx as integral ym L star yn dx plus j ym yn minus integral ym L yn dx is equal to right hand side is lambda n minus lambda m integral r ym yn dx. So, what I do, I put u is equal to yn, u is equal to yn and v is equal to ym. Okay. So, then expanded the first function in terms of its adjoint variable. So, in terms I just wrote this one in terms of adjoint operator in the form of this and we will be getting this. So, we have already proved that Sturm-Louiville operator is L is equal to L star is a self adjoint operator. So, I can and j ym and yn is equal to 0, that we have already proved earlier that Sturm-Louiville operator is a self adjoint operator. Using that condition we can write integral ym L is equal to L star. So, yn dx minus integral ym L yn dx is equal to lambda n minus lambda m integral r ym yn dx, and this was off because of this, and these two will be equal and opposite. So, you will be having lambda n minus lambda m multiplied by r ym yn dx is equal to 0. So, lambda n and lambda m are two distinct eigenvalues. So, lambda n is not equal to lambda m. So, this cannot be equal to 0. So, what is left is this integral has to be equal to 0. So, therefore, integral of r ym yn dx is equal to 0. So, what this means? This means that eigenfunctions are orthogonal functions with respect to weight function R x. This is known as the weight function. So, let us summarize whatever we have done. We have defined a standard eigenvalue problem, and we have looked into the properties of the standard eigenvalue problem, and we have proved that standard eigenvalue problem or Sturm-Louiville problem is a self-adjoint operator or self-adjoint problem. Here L is equal to L star and B is equal to B star. Then we have looked into the properties of the standard eigenvalue problem, which we will be using quite often in our course. Number one property is that it will be having infinite number of eigenvalues, and so it will be talking about a infinite dimensional space. So, it will be almost a continuous space. So, therefore, second important property is that if the eigenvalues are distinct corresponding to eigenfunctions, and if eigenvalues are distinct, then the eigenfunctions will constitute a set of orthogonal functions with respect to the weight function r. If the equation is in the form of L u is equal to minus lambda r u, then r can be identified as the weight functions, and the corresponding eigenfunctions will be orthogonal to each other with respect to the weight function r. Now, in the Cartesian coordinate system, we have seen the corresponding equation is d square y dx square plus lambda y is equal to 0. So, here the weight function r is equal to 1, and this equation is a special form of standard eigenvalue problem, where a0 is equal to 1, a1 is equal to 0 and a2 is equal to 0. So, we got the corresponding equation in the Cartesian coordinate system as a subset of the standard eigenvalue problem in its general form. So, we have talked about we have considered the general form of the standard eigenvalue problem or the Sturm-Louiville problem, and established that it forms a self-adjoint situation, a self-adjoint system, and we have looked into the various properties of the self-adjoint operator, and now we are in a position to start with the actual problem using separation of variable type of solution. Thank you very much.